Yeah, it was what, like the planner? I got expected. And I like how it doesn't have the signer on it. So you start right now. And then, yeah, it's right next to the windows. In the office section. And then they even have like, I gotta go to see what I had. Yeah, it's okay. And then I also got my friends, they have journals. I got my friend. Oh my god, let me show you my. Let me show you.
We're just here now.
My friend's gift basket, and then I got her a bunch of other stuff. I wonder if I took a picture. No, it was my best friend who lives here. It was her birthday, and then so my friend from Texas, who is here. I'll show you. When she came and flew down from Texas for my cousin's birthday. Yeah, it was really sweet. Well, this is like the start of it. So I got her like the journals, and then I also got her what's called a journal, like a bookmarks, and then I also got her her favorite book too from this like book series. And I got her a blanket, and I got her some slippers, and then they were having like $10.
Okay,
Like $5, so I got her like a
let's get started.
That's such a cute scene.
because it's so personalized. And it's so cute.
So this 5-step model, there's a lot of information in it. And make sure that all the things that I've described for you related to ventilation are all underneath step number 1. And now we've transitioned to think about what determines gas transport. There are 2 primary factors that determine gas transport: cardiac output and the oxygen content of the blood. There's a huge story waiting for you under A. Huge, huge, huge story in terms of cardiac output. But for us right now, since we're in respiratory physiology land, we're focused on factors that determine the oxygen content of the blood. And there are 2 primary factors that determine the oxygen content of the blood. One is the concentration of hemoglobin, and the other is the percent saturation of hemoglobin. And to better understand the percent, what determines the percent saturation of hemoglobin, we're now focused on the O2 dissociation curve. So what I'm trying to do is help you figure out where all this information fits into this 5-step model. And you need to know that to address issues related to this, you have to turn your attention to the O2 dissociation curve. And I gave you some textbook values downstairs. So now we're going to continue the discussion. So here's our O2 dissociation curve, but this curve is not static. It can shift to the right, it can shift to the left. Can you guys see the difference between those 2 curves back there? Good. The O2 dissociation curve can shift to the right. So here I'm just going to put underneath this arrow, I'm going to put right, shift. And so what causes the O2 dissociation curve to shift to the right? And the answer is that an increase in temperature will cause the curve to shift to the right. An increase in the partial pressure of CO2 will cause the curve to shift to the right. A decrease in pH will cause the curve to shift to the right. Ms. Jocelyn, by definition, what causes the pH to move to a lower value?
Decrease in hydrogen ions.
That's exactly right. So you said a decrease in the concentration of hydrogen ions, right? Are you saying I'm wrong? She's right now, she's thinking, yeah, I'm wrong a lot in this class. Remember, one of the things I said earlier in the class is that the pH scale is an inverse scale that describes the concentration of hydrogen ions. So if the concentration of hydrogens goes up, by definition, pH goes down. And I learned this because she took me outside one night, she had a lecture with me on all this stuff. Tell me how long. So when we say a decrease in pH, what we're really saying is that it's an increase in the concentration of hydrogen ions. Make sure you understand this. It's not the decrease in pH that creates the increase in hydrogen ions. The pH scale is just a scale to describe the concentration of hydrogen ions. It's the increase in the concentration of hydrogen ions that causes the pH to go down. Andrew,
Yes.
one of our fundamental principles, night one in our class, was what?
Structure determines function.
Structure, we're back to that. Tired old saying, structure determines function. What about hydrogen ions?
They will react with the protein structure, altering them, which changes their function.
Alter the primary structure of the protein, right?
Yeah. Secondary or tertiary?
What's that?
The secondary or tertiary?
Oh, the secondary tertiary structure, that's correct. So the concentration of hydrogen ions will affect the structure of proteins, and we're really concerned about the tertiary structure, right, the three-dimensional structure, because that's the true functional structure of proteins. And so yes, and it turns out globin is what type of a molecule? It's a nucleic acid, it's a fatty acid, it's a sugar, what is it? It's an amino acid, right? Right, that's what globin is, it's an amino acid. It's a protein, that's exactly right. So globin is a protein, and as such, it's sensitive to both, Mr. Biochemist,
Sensitive to both hydrogen
and
ions and OH ions as well.
what else is up there on that board?
Well, temperature.
Temperature, that's exactly right. So for us, we're talking about the concentration of hydrogen ions and temperature. That's why that curve is changing its shape, is because the increase in temperature, the increase in the concentration of hydrogen ions is changing the structure of globin, and therefore the binding of oxygen to the hemoglobin molecule. That's pretty cool. That's a great example of structure determines function. Kent, you're gonna tell us where in this diagram over here might these things occur? Does that happen here, 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 somewhere else in that diagram?
Is it occurring in the lungs?
Okay, you said in the lungs. All right. Ms. Camilla, what would you answer me? Circulatory system, all right. Mr. Vargas, what would your answer be? Let me help you out. Where is heat being produced? Is that being produced in the lungs? Is that being produced in the circulatory system?
I'd say circulatory.
Okay, all right. This way, what would you say? Don't know, it's fair enough. Mr. Curry, our biochemist, he's gonna tell us the right answer.
Yeah. I would see the cells.
Yes, in the cells, right? Because the cells are doing work. They're having to maintain electrochemical gradients. The muscles are contracting. And when the muscles are contracting, they are churning up ATP at incredible rates. As I've already told you, no joke. When I do this movement right here, my biceps brachii, I used up 10 to the 15 molecules of ATP. And all of you know that if you go to 24-Hour Fitness or LA Fitness or what's some other good fitness places? Orange Theory. Come on, help me out. What's some other places? Anybody go to any? Planet Hollywood. Planet Hollywood's where you go to do the opposite of getting fit, right? Okay. You're at the gym working out. You're on the treadmill, you're on the cycle ergometer, you're on a rowing machine. Geez, after a few minutes, all of a sudden, there is this stuff that begins to appear on your arms and legs, possibly. What is that?
Sweat.
Sweat. And why is the sweat there? Well, it's because as your muscles are going through these cyclic contractions, they're burning up tons of ATP, which is producing tons of heat. And that tons of heat is going to alter the structure of our hemoglobin molecule. And the thing that's cool about this is that that's not happening here, that's not happening there, it's not happening here, but here's our muscles down here, which I'm not drawing, that's where it's happening. Now, here's something that's really important to think about, and that is the slope. Yes, Maria, I saw you raise your hand, and I'll come to you in just a second. The slope of that curve represents what?
The change.
The what?
The change of the change.
Andrew, what would you say? What's the slope of that curve represent?
Not too sure.
It's okay. Kent, you'd say what? No. Kaylee, you'd say what? Mr. Cal, you'd say what?
I would say that it represents how easy it is to unload or upload oxygen onto the hemoglobin.
Okay, don't know if you heard what he said, but he said it represents the ease with which oxygen can unload, excuse me, hemoglobin can unload oxygen, right? Is that what you said? In a sense, that's true. Here's what I would tell you, is that the slope of that curve represents the affinity that hemoglobin has for oxygen. So let's just take these 2 points right here. So this delta reflects the affinity that hemoglobin has for oxygen. When the curve shifted to the right, what's happened to that slope? Is the slope the same? Is the slope higher? Or is the slope said to be slower or lower? I'm hoping that all of you would tell me that the slope is definitely much greater in that. No. Did I tell you I've got this neurological thing where I reverse things often? Yes, you're right. The slope is less. That slope reflects, you're all writing this down, right? The slope reflects the affinity that hemoglobin has for oxygen. Maria. So here's our blood, and we're going to say that that solid red curve represents arterial blood. This dashed kind of purplish line reflects what's going on in the capillary level. Your muscles are active. They need more oxygen. Do you want the hemoglobin to hold on tightly to the oxygen, or do you want it to alter its structure and give up oxygen more readily?
I wanted to give up oxygen more readily.
That's exactly right. So let me restate what I said before. The slope of that curve reflects the affinity that hemoglobin has for oxygen. And so when our muscles are active, this arterial blood flows into the capillary bed of the active muscle, and the O2 dissociation curve is shifted to the right. And you're all going to tell me that that means that the affinity the hemoglobin has for oxygen has gone down. That means that the hemoglobin is giving up oxygen more easily. That's exactly what we want. We want to provide the working cells of the body easy access to oxygen. I think that's pretty cool. Yes?
So basically, because of the increase in temperature and all of the ways to alter the structure, we're going to shift it to the right, thereby affecting the affinity.
That's correct. Except, let me just add to it, it's not just temperature. It's because when our muscles are metabolically active, they're producing a ton of hydrogen ions. So it's a combination of these two factors that's causing that curve to shift to the right. And the shift to the right due to a change in the concentration of hydrogen ions is known as the Bohr effect. B-O-H-R, the Bohr effect. Bohr. You know, if you have a background, a strong background in chemistry, that may mean something. Because good old Dr. Bohr was an exceptional chemist and biologist and physiologist way back, early 1900s. There's a model to describe the movement of subparticles of atoms. It's called the what? The Bohr model, yeah. So when you sit there and take your chemistry, they represent an atom as having a nucleus, and you've got these nice little, what do they call them? The electrons are floating around and they're called what? Orbitals. What? What was your answer? Okay. Anyways, that representation is the Bohr model. This guy was a phenomenal scientist. Huge, huge scientist. All right, so what you're seeing here is occurring down here. And just to emphasize, you understand that a right shift changes the affinity that hemoglobin has for oxygen and causes hemoglobin to give up oxygen more freely to the metabolically active cells of the body. Miss Lake. If the curve can shift to the right, you might sit there and think, well, maybe it can shift to the left. Where's that left shift occurring? I think personally, it's occurring here. Or maybe over here. If you don't know, you can always guess. But beware. Like Mr. Bennett, I can see you this. Jocelyn won't look at me. You guys are staring me down. I'm kind of like, yeah, go ahead, Ashley. Yeah.
No.
We got that. Then you want to ask Mr. Bennett, right? Sure. She said sure.
I'll say it, validation.
Mr. Oh, Andrew's gone. Yep. So you're saying yeah?
At least there. I don't know about the whole left, at least where gas exchange.
Well, where is the place in the diagram where you want the hemoglobin to have a strong affinity for oxygen? Where would that be in that diagram? The lungs, right? Because there we want it to pick up oxygen. So this is really kind of cool biology, is that at the level of the lungs, we're going to alter the structure of the hemoglobin molecule so it actually has a stronger attraction for oxygen, because that's where it's capturing the oxygen. And by the way, at the level of the lungs, what are we doing with CO2, Mr. Vargas? So where's the CO2 go? Out into the air, right? And oh, by the way, CO2 does control the concentration of hydrogen ions. So here's this very important chemical reaction, and it says the following. It says that CO2 plus H2O reacts to form what, Mr. Curry?
Carbonic acid.
carbonic acid, I forget the formula for that. It's H5CO7 or something like that.
I'm gonna go with HCO3. Cause that balances out a bit, it has to be an acid. And then plus hydrogen.
Is it H2CO3, is that it?
Yes. Do that.
And you said this is carbonic acid, right?
I don't think in that form, but I'll say yes.
I'm just writing what you're telling me to write. That's going to react to form what?
Just HCO3 and dissolve when the hydrogen's coming
Very good. So HCO3 plus a proton, right?
Yes.
Very good. Excellent. What is HCO3 known as?
Carbonate.
Bicarbonate ion.
Oh.
Where does that reaction occur? Does that reaction occur here in the pulmonary capillaries? Or does it occur here in the capillaries of the tissues? Take a look at the direction of those arrows. Mr. Lummy, where's that reaction occurring? Is it occurring in the pulmonary capillaries or the capillaries of the tissues?
I believe it's happening in like the systemic capillaries.
It's happening in the what?
In the systemic capillaries.
The systemic capillaries? So you mean the capillaries of the tissues of the body, right? What do you guys think? Where's that CO2 coming from? I made this point when we were talking about cellular respiration. Where's that CO2 coming from? Miss Elizabeth?
Air.
No. There's very little CO2 in the air that we breathe. Where's that CO2 coming from? Oh, it's gonna be going, no.
The cells and mitochondria.
Okay, he says the cells and mitochondria. Help me out here. I need a little bit more information.
Is it the citric acid cycle?
What's that?
During the citric acid cycle?
Ah, so we're talking about cellular respiration. So we have pyruvate coming in, and when pyruvate comes into the mitochondria, it is broken down into acetyl coenzyme A, and a byproduct of that reaction is the production of 2 molecules of CO2. It then enters into the Krebs cycle, and we produce 4 more molecules of CO2. So the air that we breathe out of the lungs is rich in CO2. The air that we breathe in is poor in CO2. Where's the CO2 coming from? It's a byproduct of cellular respiration. Where in our model is cellular respiration taking place? It's occurring here. And Mr. Curry told us the temperature affected the structure of proteins. And we added on to that at the level of the cells, we're also producing hydrogen ions. Where are those hydrogen ions coming from? And the answer is this chemical reaction right here. Because as a result of this reaction, at the level of cells, we're producing hydrogen ions. That reaction can go to the right, but it also can go to the left. So let me do this. If everybody will just look at what I'm going to put here, I'm going to put an increase in CO2 drives this reaction to the right. And down below, under these blue arrows, I'm going to put tissue. And where we have the red arrows, how are we going to get this reaction to be driven to the right? Excuse me, to the left. How do we drive that reaction to the left? And that's where our gas exchanger comes in. Because our gas exchanger is removing CO2 from the blood. So at the level of the lungs, we're reducing CO2, and that causes this reaction to move back to the left, reducing. If we get that reaction to reverse itself, we're going to reduce the concentration of hydrogen ions. So up above these red arrows, I'm going to put lung. Yes, go for it.
So the left shift is occurring at the level of the lung.
That's exactly right. Because at the level of the lung, we're getting rid of CO2. At the level of the cell, we're putting CO2 into the blood. So at the level of the cells, we drive that reaction to the right because we're putting CO2 into the milieu of the cell, of the interstitial fluid of the blood. That's pretty cool, don't you think? And what's really neat about this is that we're regulating the affinity that hemoglobin has for oxygen. So we're constantly oscillating where we're at in the O2 dissociation curve based upon where we're at in our 5-step model. Give me just one moment here. Okay. So, here's what we're going to do. Yes, sir.
When it comes to shifting left, the decrease in the pressure of CO2 is what plays a major role in what happens at the lung.
So, what that means is that at the level of the lungs, we're blowing off CO2. What is the term that we use to describe CO2 or O2 in the blood? And the answer is partial pressure. But what you have to appreciate is that measurement of partial pressure is really a surrogate measure for the concentration of oxygen or CO2. So really, what we're doing is we're removing CO2 at the level of lungs, which it really means we're reducing its concentration. And that drives that equation back to the lung.
Thank you.
Yeah, it's cool, huh? To me, it's fun to sit there and to learn about this stuff and begin to appreciate how we've got this molecule. Remember, first night, I told you, our biology is a miracle. How the heck is it that we've got a stupid protein whose job is to carry oxygen, and somehow it's evolved over time where it can oscillate from low affinity to high affinity? How does that happen? That's amazing stuff. Okay, one last part of the story, and then I'm going to shut up and we'll get into the lab for tonight. Well, I really won't shut up. I've got to talk about the lab. So in respiratory physiology land, there's a term that's used called the P50. And the P50 simply is an expression of the partial pressure of O2 where hemoglobin is 50% saturated. So this 50 is in reference to the partial pressure of oxygen where the percent saturation of hemoglobin is 50%. So how do we figure this out? If everybody will just look up here at the board for a moment. The P50 is a measure of the partial pressure where the hemoglobin is 50% saturated. So we simply start here at 50%, extend a perpendicular line on over to where it intersects that O2 dissociation curve, and then we draw a perpendicular line to the x-axis, and this is our P50. And Mr. Cow, in this example, what would your guesstimate be of the P50?
30 millimeter mercury.
A reasonable guess. You said about 30. In reality, it's somewhere around 27-ish, but yes, totally agree. Now, why do we care about the P50? The P50 is a simple measure that describes for us the affinity that hemoglobin has for oxygen. And the lower the P50, the higher the affinity. Let me show you. I can say this with absolute certainty. Well, parts of it may not be exactly certain, but there was that magical moment when your mother and your father locked eyes on one another. And in a spark of time, you were created as a single cell. Shortly later, 2 cells, 4 cells, 8 cells, 16 cells. Whoosh, life happens. And next thing you know, you got this fetus inside the mother. Here's the thing, is that fetus is unable to breathe on their own. They need mom to deliver that oxygen to them. But this fetus, this baby, has got all these organs, it's got its own blood. What do you think? In fetal blood, do you want to have a hemoglobin that has a high affinity for oxygen or a low affinity for oxygen? Say it. High affinity, that's right. So as you'll learn next week, there's different types of hemoglobin, one of which is called fetal hemoglobin. And fetal hemoglobin has a high affinity for oxygen. And the O2 dissociation curve is shift way to the left. So here's our normal P50 for any one of us in this room. Our P50 is right around about 27 millimeters of mercury. But here's the O2 dissociation curve for fetal hemoglobin. And Mr. Kopp, what's your best guesstimate the P50 would be for this different type of hemoglobin? 12. Oh, he's got a highly calibrated eye. Good. Typically, the fetal type of hemoglobin has a P50 of about 7 millimeters of mercury. And that means that fetal hemoglobin's got a very high affinity for oxygen, unlike our adult form. So P50 is a measure of the affinity that hemoglobin has and simply stated, the lower the P50, the greater the affinity hemoglobin has for O2. Well, there's a fair amount of stuff in this 5-step model. Question? Have you asked?
Does exercise shift the curve?
So his question is, does exercise shift the curve? Acutely it would, because exercise will cause a shift to the right. So while you're working out, as I already showed you, physical activity through an increase in temperature, increased production of hydrogen ions is going to cause the curve to shift to the right, and that will decrease the affinity hemoglobin has for oxygen at the tissue level, which means at the tissue level, the P50 is a lot higher. That means that the affinity hemoglobin has is a lot lower. But you're asking, I think, in response to chronic training, right? Is that what you're talking about? If I go out and I work out, do aerobic training for 15 weeks, is that what you're talking about? Or are you talking
I
about
was
just
asking about acute.
talking about me?
No, acute.
Acute, yeah, so acute. So acutely, yeah, because it's going to produce this shift to the right. So that happens every time your muscles become more active.
How would it be chronically for someone who does work out for a long time?
Yeah, and so the answer is that chronically, we don't change the properties of hemoglobin, so we wouldn't expect the P50 to be different in a, say, an endurance athlete. Yeah. But acutely for you, for me, for the endurance athlete, if we get on a treadmill and we start running, yeah, or at the tissue level, our curve is shifting to the right. So the P50 changes there. At the level of the lungs, the P50, the O2 dissociation curve shifts to the left, and there the P50 is lower. Does that help you? Yeah,
The chemical equation on the board that's happening in the blood.
correct. That equation is happening in the blood. All right, let's take a 5-minute break, and then we'll get going on the lab.